Then if you walk like this, if you walk like this, at some distance you will hear very loud music. At some distance you will hear almost nothing. I don't know you have realized that or not. So if you go to like some party or something like that, some musical concert, usually they put like two speaker, okay, and then so it's playing the same music, okay, because you have like a source gonna be one, but you are divided in like two speakers. That gonna be two source, okay. And if you are playing some like a music, right? I mean like some famous singer, and if you have to be exactly in the middle, okay. And then if you walk, at some point you will hear really loud music. At some point you will hear almost nothing, okay. So that is happening because of the whether you have a constructive or destructive interference. Okay. So over here, whether what kind of signal you will hear at this point depends on how far the source one and source two travel to reach you. For example, the source one and source two, they are identical speaker, but source one travels a path of 2.75 lambda. You have a path difference. So the source to travel L2 equal to, you have a 3.25 lambda, and you have a L1 over here, you have 2.75 lambda. So if we take a look on the path difference, which is delta L, I just say L2 minus L1. Then, if you subtract this one, it will be 0.5 lambda. Okay, which is going to be lambda over 2. Lambda is the wavelength of the light, or the wavelength of the sound over here. So whenever the sound reaches at the point where you are standing over there, so source one has a minimum over there. If you take a look at that way. But the source two has a maximum. So basically it's the same thing like this. One of the wave has maximum and the wave has a minimum. You will have a destructive interference at that point. They have the same wavelength. They have the same music you are playing. But even then, you have a destructive interference because the source, they travel different distance. So basically you can have a constructive or destructive interference. Not only they are out of phase or in phase, there's one condition. If you have a path difference as an integer multiple of 2 pi, lambda over 2, then you have destructive interference. So you have constructive or destructive interference based on path difference as well. So if you have a path difference of delta L, it is integer multiple of lambda, n equal to 0, 1, 2, you can have a plus minus, it's up to you. Then, which is the same as, so it's a 0, 1, sorry, not 1 means like a lambda or 2 lambda, then you have a constructive interference. So if you have a delta L, it is the integer multiple of n plus 1 over 2 lambda. So n is again 0, 1, 2, keep on going like that. Then you have a destructive. So you have n equal to 0, which means, so lambda over 2. You have n equal to 1, it will be 1 plus 1 over 2. It will be 3 over 2 lambda and 5 over 2 lambda. You keep on going like that, you have constructive, this time you have a destructive. Okay? So at this time you have destructive interference. So basically, so definitely you can talk about whether they are in phase or out of phase, but the path difference, if you are a source, they are a little bit far away from each other, then it also introduces whether you have a constructive or destructive interference. For example, why you are listening like that, like a destructive interference over there? Because your path difference I just calculated is like a lambda over 2, and lambda over 2 is the constant for the destructive interference. Okay? So you can describe the same physics in terms of path difference or like the phase difference. Okay, so this is the A. So any question before I proceed further? If not, I can talk something very interesting, very important thing over here. So basically, this is just to like ignite like some vibes on you. So this is something that I see most of the time. These are real track over here. So physics is like something like it's interesting because like you want to describe something that you see, okay, around you. So you have a railway track, okay, and then they are parallel because like railway. If you are parallel, then basically you have a derail. Basically your rail is gonna be derailed, okay. Here, take a look. They are parallel. Parallel lines in the physics means that, or geometry means that, you have two lines. They never touch each other. You have an equal distance at each point, and they never touch each other. And this is one of the examples. Like if the railway path is very like a straight, it's an example of parallel lines. Okay. But take a look on that. So if you take a look on that, even if they are parallel, it appears that they are touching. So in the physics, whenever we describe something, do not assume that the parallel lines, like they never touch each other. They touch each other at infinite distance. So that is like that concept we generate over here. So whenever we describe some physics, sometimes we call, hey, they meet each other, but that meet each other at infinite distance. So if you talk about infinite, that's like a very large number. Okay, in the physics, if you cannot describe how big is the number, then we call it infinite. Okay, so basically, so later on, whenever I introduce one like an experiment, I'll talk about, hey, they are parallel lines, but they are touching. Okay, so at that time, don't be surprised because the parallel lines, when you assume that they touch each other at infinite distance. Okay. Anyway, so I'm going to talk about this very, very interesting experiment. And this is the first experiment that proves that light is a wave. Okay, so do you remember that whenever light was discovered, I told you that there are two kind of like two group of scientists. Hey, light is a particle, and even like a famous scientist, he was in the side of, hey, light is a particle, and then some people they think that light is a wave. Okay, and you cannot argue without any experimental evidence. You can argue something, but you need to have some proof. Okay, for example, you call that, hey, today was I missed the test, or I missed the class because we have a heavy snow and then my car break down. Most of the time, I get an email from a student, hey, I cannot make it today because something happened, and then I will show up in the class, something like that. But you need to have some evidence. You cannot make some argument or some statement without any proof. Okay? So over here, whenever people are discussing, hey, light is a wave, you need to show something light is a wave, and this is the first experiment that Thomas Young did to prove that light is a wave. Okay, so this is extremely important. So if you take optics class, this light or wave, you should know this one, the Young's double slit experiment, and I will describe this one to you. So let me describe what is the Young's double slit experiment. Okay. Let's take a look over here. So let's take a look. What is the Young's double slit experiment? So Thomas Young, he did this one in the 18th century. It's a long time ago, and I'm really surprised. Even at that time, he came up with such a brilliant idea to show that light in the wave. And so this one is a little bit simple, but at that time it was so important at that time. So what the Thomas Young did, he had some construction like this. Okay, in the experiment you need to design the experiment. Whenever he designed the experiment, okay, he designed like this. Okay, so he passed the light through the single slit. It's a physical barrier. Okay, either you do this kind of experiment in the lab or not. Do you do this kind of experiment in the lab? Do you have this kind of experiment? I think we don't have it. So basically, this is a single slit. Single slit. So this is a physical barrier. You have a small opening over here. That only through that opening the light can pass through. I just say S0. Okay? So you send the light, you can send like monochromatic light, okay? So the monochromatic means you have the same color. I mean, let's say I just put like a red color for simplicity. This is a light, okay? This is the wavefront of light, and this is the direction of propagation, ray. Okay? And you send the monochromatic. Chromatic. Chrome means color. Mono means single. You have passed the light of single color. Okay, you should pass the light having the same frequency or a single frequency or single wavelength. And over here, I just draw this vertical line. That's a wavefront. And you know that light can be a ray. I mean, any wave can be described by wavefront and ray. Ray means the direction of propagation. The wavefront means the locus of point are in the same phase. If you remember, we went through that one. And we have the wave that has line or like a pen like a wavefront. That means your source is very far. You remember that, if you have a source that generates the wave, if you are closer to wave, your wavefront is going to be circular, right? If you go further, you need to draw a circle of bigger radius. And if you go even further, you have to draw bigger radius. If you, at some point, it's gonna be like a line. The wavefront becomes like a line. So if I draw a light that has a line like a wavefront, then that means your source is very far. Okay, source is very far. Okay. So let's say like a sunlight coming from the sun to earth, it travels such a large distance. Then whenever it comes over here, the wavefront looks like a line. Okay, so basically assume that source is very far away. So whenever I draw over here, this is a monochromatic light. It has a single wavelength or frequency. Okay, you can talk about frequency as well. Okay, and it's traveling in this direction. Anyway, you have this scenario over here. You have a physical barrier. That means the light cannot pass through this section of the physical barrier. The light will be blocked. There is a one small opening over here. Through that, light can pass through. Okay. So once the light passes through this one, you have it's a point source. Because this is a point source over here, it produces the circular wavefront closer to the source. Okay. Now he came up with the smart idea. Now he passed the light through the Now she passed through the two slit. It's called double slit. They're identical slit. Okay, I just named it S1 and S2. It doesn't matter which one is S1 because they are identical. S1 and S2. Just for simplicity, I just say it's S1 and S2. You have a double slit. Okay, double slit. So nothing gonna happen if the light passes through the single slit because you have only one thing happening. You have like a circular wavefront, and then after a far distance, you're gonna have again line like wavefront. Nothing happens. No magic happens over here. But magic happens if you have a two source now. Okay, so light can pass through this one. Light can pass through this one. You have a two source now. Okay, so if you have a two source, you have a chance that you have a constructive or destructive interference. Okay, now let's take a look over here. So they are identical source. I mean opening over here slit. So they have a same color. So for simplicity, to show you the interference, even if they are identical, I'll represent with a different color so that you will see the difference like this. Okay. Source 2, let me represent with that. All this like a same color, I represent something like different color. Okay. So just to show you, but visual effect. Okay. But you can see that over there in the screen that how the experiment is done and how the wave look like. So over here, the light from the source S1 and S2, they interfere over here. See, they mix together. Okay. Now, Thomas Young put a screen over here. Like that. This is center of the screen. This is screen. Definitely light can, pass through this one and they hit on the screen. And he found an alternate maxima and minima fringe on the screen. So this is they have same width, but they are alternating. This is the center of this slit, so it's called central maxima. It's always maxima. Central maxima. Okay, so central maxima. And you have a minima. This is like I represent with it's a minima. It's a maxima. The maxima. You have alternate maxima and minima. Some people say dark and bright fringe. It's the same thing. The maxima means like it's a bright. Minima means you have a dark. Okay, but you have an alternate maxima and minima fringe on the screen, just above and below the just above the and below this center point. Okay, so it's like symmetry kind of thing. Okay, so if you have a central point, we call this is the central maxima. The first maxima, the second maxima. So if you want to categorize the central, we call it n equal to 0. N equal to 0. That means we start counting. The central, n equal to 0. This is the first maxima, n equal to 1. First maxima. So you have another maxima over here, n equal to 2. So this is the how you start numbering. The n is called order of maxima or minima. So basically, you have m equal to 1, m equal to 2, m equal to 3. Okay. So this is the how you do the numbering. Okay. So he saw an alternate maxima and minima on the screen. Okay. And this was like something that the people have never seen before. it's like a very extreme, like like very exciting, like a phenomena, physics phenomena over here. And what is the reason that you see a maxima and minima pattern on the screen if you send the same source but through the double slit? Okay, if you have a single slit, nothing happens. Okay, if you have a two source, then why you have maxima and minima on the screen? And like it's an experimental physics. I also am an experimental physicist. I do the research on superconductivity. If you see like something very exciting, like something that people have never seen before, then you start to think that why it is happening. Okay, I don't know, you may or may not know. How many of you guys know what is superconductor? You may not know. A superconductor is a material. I'm a little bit distracted from here, but just spend like a few minutes. So superconductivity was discovered in 1911. Okay, it's a long time ago, almost 100 years before. Okay, and the person who discovered, so he was the Heike Onus. He was from Netherlands. He's a gas physicist. He was trying to study how the material behaves at low temperature. Okay, and he was trying to measure the resistance of the material, and then how the resistance decreases because of phonon and other scattering mechanism. Okay, but he was trying to measure like something like a mercury. Okay, mercury, and then whenever he measured the resistance is a function of temperature. Okay, so temperature. So this is the temperature and the resistance. Okay, over here he saw that the resistance decreased slowly, and then at some point he saw suddenly the resistance goes to 0. So if you go below this one, the resistance is 0. Okay, so we call this a critical temperature. Okay, critical temperature. For mercury it is 4.2 Kelvin. So if it's a mercury, if it is like a normal metal, let's say copper or platinum or something, then resistance decreases like this. Okay, it's a decrease, like something like that. At some point it's saturated, you have a finite value. It has some finite number. Let's say R is small, but it still has some finite value. But whenever he measured mercury, it hit the 0, and then even if he goes lower than that, it keep on 0. Okay, and he thought, hey, maybe like I made something wrong, because no one has seen this kind of experimental observation. Okay, and sometimes if you are a first person, like to discover something, you have two challenges. Like you have to explain this one. Either you have to forget, okay, I made a mistake, I am not going to go back. I made a mistake, I think that should be wrong. Or you need to think about, if you want to be really good physicist, or if you want to be really good scientist, you have to think, hey, I didn't make any mistake, but it should be real because I can reproduce. You reproduce several times. Okay? And he confirmed that, hey, this is, like I didn't make any mistake. So it's a real thing I observed. So basically, the copper is a very good conductor. Copper, platinum, gold, they are very good conductor. Very good conductor. But it has some finite resistance. They are very good conductor. So if you consider power loss during the power transmission from the powerhouse, it will be I square R. I mean, you are engineering people, you know what is the power transmission. You produce the hydropower or nuclear energy or something, and you bring that to the city to light up the light over here. Okay? Whenever your power transmission happens, if you have a finite resistance, you have a non-zero value of power loss. But if you have a material like mercury, and if you are in this region, what is the R value? 0. That means the power loss is 0. Okay? And these are conductors. It conducts electricity very well. We still use like copper wires a lot. Okay? But anything better than this conductor we call superconductor. Super, they are most, very efficient conductor, okay? We call mercury, he gave a name, hey, this is superconductor. This is how the name was generated at that time. Superconductor. Okay? And it's a very important because, so we generate the energy over here, like there's a nuclear plant, diesel plant, hydropower, solar power over here, or like we have a wind turbine over here. But you produce the electricity somewhere and you bring it to the city. Whenever you transmit the power, you always lose this amount of energy. But if you use a very good conductor, you are losing the power during the power transmission. But if you use this superconductor, the power loss is going to be zero. So one of the surveys shows that you are spending billions of dollars every year for the power transmission. Okay? So basically this is the idea of superconductor, how it was generated. So it's a long thing, but long story short, so whenever in experimental physicists, like discover something, you have a challenge to describe what is happening. So this person, like he came up with some idea, and so he discovered the superconductor. Same way, Thomas Young, he was like doing an experiment. He found the maxima and minima over here on the screen, and he could explain his experimental observation only after considering that light is a wave. Light is a wave. Light is a wave. Okay? He could explain only after considering that light is a wave. If you have a constructive interference, then the wave has a maximum over here. If you have a destructive interference, you have a minimum. If you have maximum, minimum, because light can be as a wave, and the wave has a property that it can have a maximum and minimum depending on whether you are in a constructive or destructive phase. Okay? So from here, he could prove that light is a wave. Okay? This is an experiment that proves that light is a wave. Okay? So let me explain over here. Okay? So let me explain over here. So sorry for this distraction. So if you want to know about the superconductor, I will tell you later. So basically, how we can explain this experimental observation using the light is a wave. So you have a two source from this double slit. If you have a constructive interference, you will see the maximum over here. If you have destructive interference over here, then you will see minima, again maxima, minima, maxima, minima on the screen. So basically, he derived the formula later on. You have a two source coming over here. So two source over here, two source coming from here, like that. Okay, you have a two source, another one coming over there. Okay, and they meet at this point. But this point here, the center. So let's say the source one travels the distance of L1, and source 2 travels the distance of L2. You have L2 minus L1, which is the path difference. L2 minus L1. You have path difference. Because this point at the center, then L1 should be equal to L2. You can prove the geometrically. You have two triangles over here, and this side is the common side. And this is a 90-degree angle. You can prove geometrically that this length is equal to this length. You can do the geometry, okay? So if your path difference is 0, then according to our wave theory, if you have a path difference of 0, then we have a constructive interference. That means whatever he has seen in the center point as a maxima can be explained. Because path difference is 0. I should have a maximum over there. Right? whenever you derive something like a formula, the formula has to be valid for any point on the screen. Okay? So later on, he derived some formula that is like a valid for any point on the screen. So if the formula is valid for any point on the screen, then you can predict that whether the given point on the screen is going to be maxima or minima. So let me go a little bit faster because I have like 1.5 an hour, so I want to finish this one. So you can do that some simple mathematics over here. I just like take any random point on the screen. Let me take any random point on the screen. It's a center point. So for simplicity, this is my screen. Okay, and for simplicity, I just talk about 2 points over here. It's a double slit, okay? I just put like double slit like this. The source S1 and S2. So double slit. Double slit. So I consider this, slit S1 and S2. The distance between these two slits, small d. We can call S1 and S2, okay? And small d is the distance. And definitely this is the center point over here. And it's always maxima. But if I have some formula that will be valid for any point on the screen, that whether it's going to be max and minima. So let's say I take some random point over here. Okay, random point P. Okay, so light from the source S1 and S2. Like that. They go over there. So this is a length L1, this is L2. It's a random point P. Light from source S1 S2 travel to meet at point P and identify for maximum. Okay? So if I want to consider that this point is a maximum, then the best way is to explain the path difference. So if I want to see what is the path difference, definitely you can see that the source 1 travels smaller distance compared to source 2 to meet this point P. You can see from there. If I want to find the path difference, what you do a simple geometric construction. Just draw the perpendicular. So any point after this, they have the same distance they travel. This is the only extra distance delta L traveled by source 2 to meet point P. So my job is to find delta L and find the condition for maximum and minimum. If delta L equal to m lambda, I will have a maximum at point P. If delta L equal to n plus 1 over 2 lambda, I will have a minimum. So my challenge is to find what is the delta L. Okay? So delta L is not that difficult. So let's consider a horizontal line. And the horizontal line, it makes angle of theta over here. And it's a simple derivation that even I can use this space. Okay? So let me draw this triangle, a small triangle. I have a small triangle like this. Okay, it's a perpendicular. This distance is d because you have a source S1 and S2 over here. S1 and S2. And you have another line that's going like that. This angle is theta. You have a right angle triangle over here because there's a perpendicular you draw over here to find the path difference. This is delta L. I need to figure out. this side of the triangle. Okay? So this is a right angle triangle because you have one angle is 90 degree, and if this angle is theta, I can prove that this angle is also theta. It's a simple math. Okay? To prove that this is theta 90 degree, because if you say this is a beta, let's say it's a beta and it's alpha, you use the same method. So this is a 90 degree angle. So alpha plus beta is 90 degree. Okay. Again, this is perpendicular to this one. So theta plus alpha plus beta is 90 degree. And use the same that we used last time. Negative. This one cancel out. Beta minus theta equal to 0, and beta should be equal to same as theta. Right? It's a simple derivation. So I could prove that this angle is theta. Now you have a right angle triangle. One angle is theta, it's a 90 degree. This side of triangle is delta L. I want to figure out what is the value of that. I have given another side as a D. Okay? Now, you need to use the trigonometric function either sine or cosine or tangent to find this delta L. So if you have, this is the angle, two angles, this side of angle, this side of triangle. If you have a side of the triangle, this one that has both angle, what we call that? It's the opposite of 90 is a hypotenuse. This one, base. What do you call this side of the triangle? Anyone of you guys? Yeah, you use a little bit different language, yeah. Over here, A, D, J, and this one is opposite, right? Now, I need to calculate this one. I have given this one. So, any trigonometric function that gives a relation between this side and this side. Do you know any trigonometric function? Sine, cosine, tangent.
Sine.
Sine is equal to sine theta is equal to opposite divided by hypotenuse. It's a delta L divided by D. If I want to get delta L, you have 1, you have to do cross multiplication. It will be delta L equal to D sine. Okay? For the geometry construction, I have delta L equal to D sine theta. So now, Thomas Young did, if delta L equal to D sine theta is equal to M lambda, then I have a maxima at that point P. If it is equal to D sine theta equal to N plus 1 over 2 lambda, then I have a minima. And he did mathematical calculation, and he could predict any point. He can map any point on the screen that whether that point is going to be max or minima by using this formula. Okay, so this is the Young's double slit experiment. It's a very powerful, very interesting, very intriguing, and at that time it was so popular that and there are so many research people have come after that. Okay, so he's the pioneer of this this light is a wave. He was the pioneer for the proving that light is a wave. Okay, any question about this one? I'm going to prove that every single detail over there. Any question? The test one, there will be so many questions from this Young's double slit experiment. So I want to solve a couple of problems. You have so many problems over here. I have 1, 2, 3, 4 problems for you guys. I may not be able to solve all of them, but I can solve one of them for you. So let me start with the first one. How to approach this one. So it's a very simple experiment. You have a 1-in-1 formula. This is the formula for maxima. You have minimum formula. And it's called order of maxima or order. So order. So if n equal to 1, I call cost maxima. If n equal to 1 for the minimum, we call cost minimum. Okay? N is the order. So let's take a look on this problem and finish the class. So according to this problem, suppose you pass a light from a helium neon laser through two slits. So you have a helium neon laser. Okay, so I can keep this one over here. I just solve on other side. You have a light that is passing through the double slit, and the light is laser light. Okay, so for simplicity, you have a double slit. You have a double slit over here. I should draw it better. Let me have. So light is passing, you can draw like this, S1 and S2, okay, double slit, okay. The light is passing from here, so let me represent with a different color, so that light is from helium neon light, let the light, and it's going this way, okay. So helium neon laser, okay, neon laser light passing through this one, and it's a double slit experiment, and you have placed the screen in a far distance over here. The screen, okay. So if I consider like that, you have maxima over there, the central maxima over here. Central maxima. In the central point, I will put n equal to 0 because you start counting n equal to 0 from there, central point. Okay. So you have a helium neon laser light that's passing through a double slit, and that is separated by 0.01 millimeters. So you have a distance between the slit. I just call it small d. You have a small d over here. I call this small d. Okay. You have given this small d value is 0.01 millimeter. It's a very small narrow gap between the slits. You can change this one to meter. So you have a millimeter, so 0.01 times 10 power minus 3 meter. Okay, you can change to SI rate. Over here, find that third bright line. Okay, third bright line. So you have now m equal to 3 because the order is represented by n. So third means n equal to 3. You have n equal to 3. You have a first somewhere here, this is center. You have a first somewhere here. I'm just like first here. You have a second one over here. So second one over here. I have a third over here. So it's an n equal to 3. The bright or maximum. So first, second, and it's n equal to 1. It's n equal to 2. Okay? I'm talking about this n equal to 3 over here. That find that third bright line on the screen is form an angle of 10.95. We have given theta value. The theta value is given m equal to 3. Theta value is equal to, theta value is 10.95. Okay, and this is a maximum. Okay, so 10.95 is the angle. So 10.95 related to the incident beam. What is the wavelength of light? So basically, you have to find what is the wavelength of this light. Okay, and you want to draw the diagram. going to draw the diagram. Source, you reach over here. Source over here. You are given the angle over here. This is the angle theta you are talking about. This angle is same as this angle. So this is for the maxima. And as I told you, you have a 1 or 2 formula. D sin theta equal to m lambda for maxima. D sin theta equal to m plus 1 over 2 lambda. You have a 1 and 2 formula. And it's very simple because you can use this formula. Just for simplicity, I just here this one. We are talking about the maxima. So I just use this formula. D is given, theta is given, m is given. Can you calculate the lambda? That's the only unknown in this equation. Okay? You have lambda if you want to simplify d sine theta equal to m, and just plug in everything. Everything is given over here, and that's going to be in meter because you converted d into the meter. Okay? So this is how you solve it. It's a very simple simple problem to solve the finding the wavelength of light that is passing through the single slit as a double slit to form the interference fringe on the screen, and then you need to find the wavelength of the light. Okay. Any question about this one? If not, I want to solve one more problem. Just give a hint for you guys. You have a 3 more problems. 1, 2, 3. I can solve either of them. I mean, if you want, I can solve either of them. But in my view, this one looks a little bit challenging compared to other ones. But if you want me to solve other than this question, I'm okay with that. Other problems you have to try by yourself because I basically cannot solve all of the homework problems. But homework due gonna be next week, and then you have enough time on Monday and Tuesday to find the people around, find me in the office. You can go to help lab to solve it. So if I give a hint on this one, I think that's gonna be the point. This is a little bit challenging one, and let me solve this one. I'll give a hint at least. So I have 10 minutes, so let me grab one on this. Okay. So you have again double slit experiment. So let me draw the double slit experiment, and so this is one trick over here. If you figure out that trick, you can easily solve to find the unknown quantities in the problem. Okay. So let's go to the problem. So over here you have a Young's double slit experiment. So according to this problem, light of 650 nanometer is incident on 2 slits. So it's a double slit. Light is having the wavelength. The wavelength is given lambda over here. Lambda is given 650 nanometer. Okay. Is incident on 2 slits. A maximum is seen at an angle of 4.10. So you have one is maximum. The angle is given. Let's say theta maxima is given 4.10. Okay. You have a minima that is seen at an angle of theta minima at an angle of 4.70. Sorry, 78. 4.78. You have 2 angles for the maxima and minima that is seen on the screen. Okay. So let me draw the diagram. You have a Young's double slit. This is a very simple diagram. Your double slit. So light from the source 1 and source 2, S1 and S2. Okay. So basically travel on the screen, and the central point is always maximum over here. So maximum. Okay. So light. Let me represent another color. So light from source 1 and source 2. The travel. Okay. Over here. And the question is over here. You need to pay attention over here. Or minimize observe at angle of 4.10. So minimize at random. Okay. So let me represent minima like this over here. It's a minima over here. It's a minima. Okay. You have a minima over here. And minima is seen at an angle. Let me draw this angle. This is the line. Okay. This is a minima, you see, over here. So this is the theta minima, okay, over here, which is equal to 4.78 degrees. Now, this is a maximum, So maxima is, it's a maximum, okay? It's a maximum. The maxima is seen at some angle over here. A maxima is seen at an angle of 4.10 and the next minima at 0.78 degree. That's very, very important over here. The word is called next minima. So you can have, because you have a maxima over here, you have a maxima over here, you have a minima over here, minima, you have a maxima, you have a minima over here. Okay? So basically it's an alternate maxima and minima. Once you have a maxima, you have a minima over here, you have a minima over here. Now, the word is called next minima. The next minima means that just next to the maxima you are talking about. If you talk about this maxima, either this minima or this minima. Okay? There are two options because next means like a, if someone is like, if you consider yourself, next to you means like either you this side or this side. But which minima we have to consider over here? Anyone of you guys can tell me? I'm sorry? Above or below? Below. What is the reason that you want to go to this above?
Because the angle's bigger.
Because you have an angle that is bigger than this one. If you consider this minima, the angle will be smaller. So we are talking about this minima because if you do this one, this angle going to be 4.78 and this angle going to be 4.10. Because the angle is given bigger than 4.10, you have to consider this minima. If you consider this minima, I think you will get wrong answer. Okay? So this is the identifying which maxima or minima you have to take. You need to draw a diagram. It's already drawn diagram. You can call this is the maxima, minima. You have already angles drawn. It's a double slit. It's a double slit. Just memory. Double slit, and the screen, and this is the light and whatever light, and just have a lambda. You have to just plug it over here. That is part A, and part B and C. I have like a couple of minutes left. I don't know whether I can make it or not. Let me go a little bit further. What is the order of maximum? So I need to find order because this is central. The central maximum. You have n equal to 0. Okay. You have like m value for this maxima. Let's say m value, I need to figure out what is the maximum m order of this maximum. I need to find m. And we have a 1 and 2 formula for the maxima and minimum. Give me a second. I'll just take 1 minute, okay? So if I cannot finish it, I'll work on the next class. Over here, you have two formulas over here. I'm going to give hint. You have a d sine theta maxima equal to m lambda, and you have a d sine theta minima equal to n plus 1/2 lambda. You need to play with this one to find the m value. If I were you, I just divide this one like this. d cancel out. You have given angle value. You have given angle value on the left hand side. Sine theta minima divided by sine theta maxima. Basically, you have given left side. You have a number. So you have a lambda cancel out. You have a 1 plus 1/2 n. So in this equation, it's a number. You will get some number over here. On the right hand side, you have a 1 plus 1/2 n. So this is only one unknown in this equation. Can you calculate m? Yeah. That's only one unknown in this equation. Right? Because this is the theta minimum, theta maximum value is given. It will give you some number. Your 1 plus 2n. So you are done. So once you know the what is the m value, then you need to find the d value in the C. So we can use either equation d sine theta equal to m lambda. Lambda value is given, m value you are going to get it from the part B, and your theta maxima is given. That's a one unknown, that's d. Can you calculate it? Yeah. So try to solve it. I need to rush because of this time. But we have a next class. I'm going to try this one again. So next class will be revision class. Try to read the class, okay? If you have to miss this answer, call it to take a note. Okay, so with that, I'll see you on Wednesday.
Minimum condition.